Back at it again, guys. Today we're going to be focusing on modeling with these functions. This is section 3.3 in our book, but modeling with functions, we're going to split this into 2 days. Today we're going to focus on independent and dependent variables with a quick intro of modeling. Learning objectives for today, I can determine independent and dependent variables. And then our second one, I can model with functions. Independent variables. The independent variable is always located on the x-axis of the graph. It is our input, it is our domain value, so of course it's the x in our tables or equations. The independent variable stands alone. It does not depend on the other variable that's in our problem. The independent variable is what happens first. This has to happen before the other variable can happen. The opposite of that, dependent variables. Dependent variables is always located on the y-axis of the graph. It is the output. It is our range. It's usually the y in a table equation. This completely depends on our independent variable. And it's what happens second. Let's look at a few examples here. This first situation, it says a student's grade depends on how much she studies. This kind of gives you a big hint because of the word depends right into it. But we could break this thing down, independent versus dependent. What are the two things we're talking about in this problem? We're talking about time spent studying. We're talking about the student's grade. The student's grade depends on how much she studies. So that independent variable is the time studied. That has to happen first, then the grade happens next. If she spends a lot of time, grade's going to be better. If she spends not a whole lot of time, grade's going to be worse. Let's look at number 2. The height of a plant and the amount you water it. The height of a plant and the amount you water it. Those are the two things we're talking about. The plant and the water. Now, do you think the water depends on the height of the plant? Or do you think the height of the plant depends on the water? Hopefully, we're realizing that it's the water that's independent. You could water that thing a lot or a little, and depending on how much you water it, that's how tall that plant's going to get. If you're watering it correctly, that plant should get taller. That plant should be healthy. If you're watering it incorrectly, that plant's going to die. It's not going to get very tall at all. So there's a couple examples, independent versus dependent. Let's look at a few more. The amount of money you make and the number of hours you work. Now, some of this, guys, it's kind of easier to think of when you're thinking what comes first, what comes second. So in this problem, do you think you get paid first, or do you think you have to work first? Hopefully, we're realizing that work is your independent variable. You have to put the hours in before you can get paid. Number 2, the number of sodas you buy and the total money spent. In this problem, we're talking about sodas and the money. We have to find that number of sodas, and then that adds up to the total money that we spend. I'm not going to pay like $20 for one soda if I'm only buying one soda. I'm going to get all those sodas together, then buy it. That happens first, money happens second. Number of houses you can paint depends on how much time you have. Again, another depends in this situation. So breaking this thing down, independent variable, the amount of time. Dependent variable, the number of houses. How much time do I have? That's how many houses I can paint. Independent versus dependent variables. Now let's get into the modeling piece of it. Taking a look at this here. It says, while on vacation, your family traveled 2,040 miles in 6 days. Your average speed was 340 miles per day. Write a linear function that models this distance your family traveled each day. Verbal model, distance traveled equals our average speed times time. So now we can start putting this down with our labels. We have our distance traveled, which is our function notation, f of t, t for time. Average speed was what we got from the problem, that 340 miles per day. And then our time was in t days. We could put all of this together saying distance traveled, f of t, equals my average speed, 340, times my time, which is our input, which is t. Now with the values we have here, we could take our input time, 6, plug it in times that 340, and see if that output matches the 2040, which it does. Next one. Use the model to find the distance traveled after a day and a half. So the model that we just came up with, that equation, that function we came up with, we're going to use, but now we want to use it for 1.5 days instead of the grand total of 6. So we're going to take that 1.5 as our input, plug it into our function, find the output. 340 times 1.5 gets me 510. We traveled 510 miles. In 1.5 days. While on vacation, your family traveled 2,660 miles in 7 days. Your average speed was 380 miles per day. So again, write that model. We've got our same model as before with that distance traveled still as f of t. Our average speed this time is now 380, and our time is still t. Plugging all that stuff together, I've got f of t equals 380 times the time t. Now I could use that. For this problem here, they're asking for 1.5 day of travel. So take our function, plug in 1.5, and we can find out how many miles we traveled in a day and a half. We traveled 570. That's all I got for us today, guys. Take care. We'll talk it up in class.